Hi, my name is John Mayberry, and I'm an assistant professor of mathematics at University of the Pacific. This summer, I had the opportunity to take part in the week-long workshop on the secondary integration of math modeling and simulation in the classroom. And as we walked through some examples in the NetLogo library, I noticed that a number of them had some interesting probabilistic aspects and would be models that myself as an applied probabilist would be interested in studying. So the purpose of this and other videos is to present some of those models or highlight some of those models in several layers. The first layer will just be to introduce you to the model and where you can find it in the NetLogo library. The second layer will be to present a simplified version of the model with some simplified code that gives kind of an intuitive reason for why the model is exhibiting the behavior that it does. The third layer then is going to be a little bit more mathematical in nature, but presented in such a way that both math and science teachers can piggyback off the information to design their own lessons, which would be appropriate for the class they're teaching. And then finally, I'm going to conclude with just a few musings about some of the reasons why I find this model interesting to investigate. So the first model we're going to talk about can be found under the Chemistry and Physics folder in the NetLogo library. It's a model for radioactive decay. And to get your feet wet with this model, if we set up an initial configuration, you see all these cyan circle turtles appear on the screen, and these turtles represent radioactive nuclei. And if we run the model, we can see that as time progresses, the cyan turtles light up yellow, and after flashing, they dim in color, and the dimmed nuclei then are those which have decayed. And we can run the model until all of the nuclei decay, and you can see that in this particular example, well, it took over 200 units of time for that to happen. Now we're going to be focusing on this first graph in our explanation. This graph shows the number of surviving nuclei, the number of radioactive nuclei as a function of time, and you can see this clear exponential shape start to develop. This summer in one of his presentations, Vic Castillo of Lawrence Livermore quoted the statistician George Box as saying, "All models are wrong, but some models are useful." Now the models in the NetLogo library are no exception. So having a little bit of an understanding of how NetLogo is modeling exponential decay will help you make a better judgment as to whether you believe that it's an accurate representation of reality. So the best way to understand NetLogo's simulation is to think about coin flips. Now, a coin flip is something we're all familiar with as we've played games with them all our life. And a good model for a coin flip is to assume that the coin, when you flip it, has a 50% chance of coming up heads and a 50% chance of coming up tails. Now, to connect this to the exponential decay model, I've created an extra program which I call exponential coins. And exponential coins, if I click setup, I see a bunch of people turtles appear on the screen. And what's going to happen is every round of play, each person is going to flip a coin. And if the coin comes up heads, then with a 50% chance, which is given by this death probability parameter here, that person's going to die and leave the game. And with a 50% chance of tails then, if the coin comes up tails, they're going to survive to fight another day. Now I began with 2,500 people, just like we had 2,500 nuclei in the last simulation. I'm going to slow it down a little bit because it'll move fast. And if I click go, you see people disappear. And in this particular scenario, we again see an exponential curve, and it took 13 rounds for everyone to die. Now, the number of people, so the people here are synonymous with the nuclei in the previous example, and the death probability is synonymous with that decay chance. So for example, if I decrease the death probability to 0.03, I see something very similar to what we saw with the nuclei example. I'll speed it up again a little bit, where it takes, over 200 rounds for all the people to die off, 269 in this case. So you could think of this as saying I have a coin that's extremely biased towards tails. It only has a 3% chance of coming up heads and a 97% chance of coming up tails, and we're simulating this nuclei by these coin flippings each round. Now the code for this model, I'll include this and attach it to the video. Although the exponential coins program gives us a good intuitive explanation for how the radioactive decay process is simulated in NetLogo, it doesn't really provide us with a mathematical reason for why we would expect to see an exponential curve emerge. So to do that, I've taken an output from the exponential coins program and exported it into an Excel document. And this was an output in a situation where the death probability was 0.5. So the first example we saw where everyone is just flipping a fair coin to determine who lives and who dies. We can see down here 2 columns of output. The first column shows the dependent variable time, the independent variable time in this scenario, while the second column shows the dependent variable, which is the number of survivors during that round. I've created a third column here, which has been labeled model. And in the model column, what we're going to do is create a mathematical function which we believe captures the typical behavior of these simulations. Now, this model should certainly start out with the same number of people that we had in our simulation, but it's not going to proceed by some random fashion. It's going to proceed deterministically based on what we would expect to happen. So since we have people tossing coins, and it's a fair coin, we would expect that out of the initial people in our model, out of the 2,500 initial people in our model, we would expect only about half of them to remain after 1 round. Furthermore, if we would like to estimate the number of people remaining after 2 rounds, we would expect the outcome to be about half of what was in round 1. And using Excel's relative cell referencing, we can easily compute these values by simply dragging down the contents of cell C19. So for example, now if I click on cell C20, I can see that C20 is taking half of the previous, and then C21 is taking half of the previous, and so on. And we have generated the expected number of people surviving up until time 30. Now notice we do get ridiculous things here. For example, I obviously cannot have 0.61 people, but it's an approximation of what I expect to happen. And if you want to see how good the approximation is, we can make a plot by highlighting these 3 columns. What we'll do is we will do a scatter plot here. And notice that you almost can't see the blue line which is given by the actual data, because the model is actually such a good fit for this particular data. Now it's also fairly straightforward to see how our demonstration in Excel relates back to a familiar representation of exponential functions as functions of the form a, b to the t. In this experiment, if we start with some initial number, let's call it n sub 0 people, then as they pass through this first coin flip, as represented in this diagram below, we know that about half of them are going to survive and half of them are going to die, which means that we'll have about 1/2 and not remaining after that first coin flip. Now, of those half who survived the first round, we know an additional half are going to survive the second round, or approximately half, which means that after a second round of play, we are going to end up with 1/4 of what we originally started with. And after a third round of play, we'll end up with 1/8 of what we originally started with, and so on. And at this point, hopefully you can recognize the pattern that after n, or after t rounds of play, the number of surviving people will be about 1/2 to the t times n naught, which corresponds well then with our standard representation of exponential functions. So now we get to the fun part of the presentation. Let's suppose you wanted to estimate the number of rounds of play it would take until everyone is dead. Well, if you take this literally and assume that we use the expected equation that we derived in the previous slide, well, you could think of doing this by solving the equation 1/2 t times n naught equals 0 for t. Now, if you try and do that, you won't be able to find a solution because the left-hand side is never 0. And the reason why is kind of illustrated by one of my favorite jokes. A mathematician and an engineer have a friend who's locked in a castle, and there's this magic spell on the castle. And the way the spell works is that every time you take a jump towards the castle, you can only move half the remaining distance. So the mathematician starts off, he takes a jump, moves half the distance, takes a jump, moves half the remaining distance, takes a jump again, and a fourth jump, and then throws up his arms in frustration and realizes, I'm never going to make it to the castle, so he returns home. After he's finished with his attempt, the engineer decides to give it a go. So she takes 1 step, 2 step, 3 step, 4 step, and then she comes back with her friend. The mathematician stares at her in awe and said, how did you do it? And she said, well, I just waited till I got close enough and then I grabbed her. So you could use the same philosophy in the previous problem, and instead of solving this equation, figure out the time t until there's 1 student remaining, and that would give you a decent estimate of the time it will take until everyone's dead. Now, on the flip side of exponential decay are processes governed by exponential growth. Exponential growth can lead to some surprising results. Let's take, for example, the process of folding a piece of paper. Now, if you've never tried it, you should, but it's very difficult to fold a piece of paper more than 5 or 6 times. I can usually get to about 5 before it starts becoming an unfoldable wad. There was a group of students in 2011 at a high school in Massachusetts who wanted to test their abilities to fold a sheet of paper, but they cheated a little bit. They used toilet paper, and the toilet paper they used was actually 1.2 kilometers long. And even with that long of a piece of toilet paper, they couldn't get more than 13 folds. But let's suppose for the moment that we could theoretically keep folding a piece of paper. How many folds would we have to make until it reaches the moon? Now, before you guess, the internet says that the moon is on average about 384,000 kilometers away from the Earth, and a piece of paper is approximately 1/10 of a millimeter thick, which when converted to kilometers gives you, well, 1 with a whole bunch of zeros in front of it. Do you have your guess in mind? Okay, great. Let's use Excel to find out the exact answer. Well, each time we fold a piece of paper in half, we're essentially doubling its height. So after 1 fold, we have twice as much as we did originally. After 10 folds, right, that paper's still looking pretty small. After 15 folds, we've just now gotten a paper that's a little bit more than a meter. But look at what starts happening as we move down to 20, to 30, let's go all the way down to 50. Notice that by the time we've gotten to 50 folds, we have far surpassed the distance from the moon. And backtracking, it looks like it actually took 46 folds for us to reach the moon. To conclude this video, I wanted to briefly return to our exponential coins simulation and talk about this other variable, the number of rounds of play it takes until everyone dies off. You can see that the last time I ran the simulation, it took 14 rounds of play. If I run the simulation again with the same death probability and the same number of people, it takes 13 rounds. And if I run it again, it takes 14 rounds. And if I run it again, it takes 12 rounds. So we can see that the number of rounds of play varies from simulation to simulation, which makes sense since at the core, all this program is doing is tossing coins. Now, you can easily have your students and you can yourself address questions such as, what is the expected number of rounds of play that this game will last? Or what is the standard deviation of the number of rounds of play this game will last? Or what is the median of the number of rounds of play this game will last? All these can be easily investigated by running the simulation a large number of times and tracking the output in Excel, for example. Despite the simplicity of these procedures, proving results mathematically about this model is incredibly complicated, and there have actually been some advanced probability papers written to get estimates for the expected value and variance of the number of rounds to extinction in models just like this. To me, that illustrates the power of doing modeling and simulation in the high school classroom. Students can ask some questions which are of real interest to researchers and develop some rudimentary methods for investigating the solutions to these problems.